you have a problem about how fast Earth is moving, if I remember correctly. Or something, a satellite orbiting in space? Something. Or maybe I have it. We'll see. We'll see how far I'm going to get. Okay, now the big thing you have to get straight here is, what's the difference between angular velocity and linear velocity? Where they're both talking about something spinning in a circle. But you have to know the where it's spinning. If you're doing angular velocity, we are talking about, if you have an angle formed at the center, you're talking about how fast is the angle at the center spinning. That's angular velocity. When we talk linear velocity, we are talking about how fast is something on the edge of the circle moving. How fast is it moving out on the edge? So angular is how fast the center is moving. Linear is how fast the edge is moving.
So angular velocity is how fast Earth is spinning, where linear is how fast the satellites rotating around us. Right?
Yeah. Well, actually, linear is how fast we're moving because we're on the edge of Earth. We're not at the center of Earth.
Angular is how fast the Earth is spinning.
Yeah, how fast the Earth is spinning at its center, yes, that would be angular. Okay, so formulas actually are pretty common sense. You kind of would expect this. They picked a Greek letter for angular. I'm not sure why the history on that one, but okay. It's the Greek letter omega. It looks a lot like a curled in W, but it's actually omega. Okay, that's the symbol for angular velocity. Don't ask me why. Okay, this is a velocity. When you all drove to school today, how fast did you drive?
I drove like 20 miles.
You drove down 11th Street. I hope you drove 20 miles an hour. Miles per hour. Miles is a measure of what? Distance over time. Okay. So if I want angular velocity, what is the distance that angle is moving? Angular wants to know how far the angle moves. We measure an angle in either what? Radians or degrees. You're going to do radians here, of course. So it's simply how far did the angle move over how much time it took to do it. That's the formula. Angle over time. Okay. Answers for these will be something like radians per minute, radians per second, radians per hour. It'll always be radians per something when you get done with an angular velocity problem. Linear, on the other hand, though, wants to know how fast this outside edge is moving. Okay, so if I move from there to there in 2 seconds, what distance did I travel? Isn't that the arc length? Okay, so linear velocity is represented with a small v. So there's actually several versions of this formula. So you could say it's the arc length, how far did I travel over time, or to figure arc length, you have to go back to the arc length formula, which is r theta over time. That's the one you're going to use the most, right there. That's going to be the formula that's going to be the handiest for you.
What's the name that's around it?
Or, doesn't this have a theta over time? Isn't that the same as angular over here? So you could say it's the radius times the angular velocity. So if you know the angular velocity, you only have to multiply by the radius to get the linear velocity. So you can actually do it in all three versions. It depends on what they give you, the information they give you as to which is the best.
I'll just try that one. Because it's the one you use.
It's the most common. Okay. So, darn, we don't have time to experiment.
Is that the symbol or is that a W?
It's
omega.
Okay.
in the Greek alphabet.
Okay, last year, I usually have y'all do this, but we don't have time here. I had a student who had a wingspan. Their arms were 5.5 feet from our fingertip to fingertip.
I think mine may be longer.
And he did 12 revolutions. I didn't stand up here and spin. Did 12 revolutions in 10 seconds. Okay. I don't think I have time to do both. If I said what's his angular velocity, how much angle did he do? He did 12 revolutions.
So 360 times 12.
Not 360. Radians. revolution in radians, 2 pi. Anytime they say revolution, think, oh, that's 2 pi. So yeah, he did 12 times 2 pi over 10 seconds. And okay, they'll leave angular velocity in pies. That's the only one they leave pi in the answer. I'm okay if you decimalize it, but they won't. So they'll reduce that down to 12 over 5 pi radians per second. His linear is much more interesting. How fast was his fingertip moving? Okay, well, I recommend the starred one. What was his radius? If his whole wingspan was 5.5, what was his radius? Wouldn't it be half of 5.5 would be his radius? Would be 2.75, thank you.
Are you going to check our note cards?
Oh, boogers. I was supposed to. Forgot about that one. And his angle we already knew was the 24 pi, the 12 times 2 pi. He did 12 revolutions in 10 seconds. This was, think of this as his diameter. From fingertip to fingertip across was 5.5. So his radius would be half of that, half of 5.5. Once again, you're going to jam it in the calculator. So his fingertips were going about 20.7 feet per second. Think about that. 20.7. That'd be 10 of these wall pieces in 1 second.
Couldn't you have done like the R times?
Yeah, I could have done radius times this. Yeah, because I did both. I wanted you. That's the way you'll normally do it. Okay, I'm going to warn you. The angular linear part of this sum is going to drive you crazy because watch the units. They give you a problem with feet and miles. You're going to have to convert units on a couple of them. So beware of the unit conversion. They're mean to you on that problem, part of the problem.